Now let's have a look at the types of distributed systems. According to your textbook, there are three different types of distributed systems: high performance distributed computing systems, distributed information systems, and distributed systems for pervasive computing. Now, uh, if you look at more recent textbooks or published material, you might come up with more types of distributed systems, like, for example, edge computing systems and fog computing systems. Some consider edge and fog computing as part of cloud computing, whereas some other people consider them to be completely different. These are different approaches. So what I mean is, in a different context, you might see more than three types of distributed systems, but in this chapter, we're going to stick with your textbook's definition. So let's start with the first one, the high-performance distributed computing systems. So we're trying to do computing in parallel. So let's first understand the difference between the multiprocessors or multi-core systems versus the multi-computer systems. In the first case, where we have multiple processors in a computer system or multiple cores, we're talking about a single computer system where we have these multiple processors. Each might have multiple cores again, and several shared memory units, several memory modules. Now, since this is a single computer system, these memory modules are working as shared memory between all these processors. So they appear as one system, one large memory, and the processors connect to these memory modules, to any one of these, through a high-speed interconnect, which is, remember, inside the same computer. So this is quite fast. Alternatively, in the case of a multi-computer system, as the name implies, we have multiple computers. So each computer has its own processor or processors. Of course, you can still have multi-processor systems this way, but it will be a small number of processors. And also, each processor could have multiple cores again. But each one has its own memory module. Okay, so each one of these here are separate computers, actually, hence the name multi-computer systems. But these computers are typically connected over high-speed network connections like fiber channels. And they can interact with each other. They can get information from the memory of the others. As I said, these are over high-speed data links, but still the data rate here will not be comparable to what you have over here, because this is inside the same computer. So these are fully synchronized systems over a single clock, whereas these are separate computer systems that are connected over the network. So multi-processor systems, the first case we saw in the previous slide, are easier to program compared to multi-computer systems, but they also have problems in increasing the number of processors or number of cores. Actually, you're limited by the hardware. So the hardware you purchase will support some number of processors. So if you want to extend it further, unfortunately, hardware does not support it, so you cannot extend it. So there is a scalability problem there. Whereas in the case of the multi-computer systems, if you need more processing power, you will be buying more computers. And hence it is actually extensible or scalable. However, in the second case, since these are different computers running on different clocks and with different operating systems, synchronization between these machines, and also synchronization will be a problem, and also getting data from the other memory will be typically far slower. Now, to achieve this, one technique you can do is you can benefit from the virtual memory idea and merge all of these memory units from different computers into a single virtual address space. And when processor A needs some page P from the memory on another computer, let's say on processor B, in that case, actually, the operating system at A will cause a trap. It will communicate with processor B, and that will, with the computer where processor B is, that operating system will fetch that page and send it to A, and then the processor at A may resume its operation. But performance-wise, distributed shared memory systems, as in the case we just discussed, cannot compete with that of the multiprocessor systems. They're inherently quite slow. Another concept we need to discuss is it's still under the topic of high-performance distributed computing, is cluster computing. Now, in the case of cluster computers, this is actually a case of this multi-computer approach. You have multiple computers, but this time, specifically, one of those computers is serving as the master node, whereas the remaining n-1 nodes are serving as the compute nodes. Now, all the requests to start applications will come to the master node, and the master node will be managing which compute nodes will be running this specific process. So at the master node, we have the management application. Typically, this is the one that you can connect to using SSH over some remote access network. So these compute nodes are behind the master node, and they're not directly accessible from the internet. And the master node will be tracking the operation of these compute nodes and distribute the load over these compute nodes as necessary. It will have all the necessary libraries and everything. So if you need more processing power, you can just buy a new compute node and just add it to the system. The master node will immediately configure it, send it the necessary libraries first, set it up for the operation, and then also send the necessary application components for them to operate. Now, among these compute nodes and the master node, there will be typically a standard network for the general synchronization operations and control operations, and a high-speed network for data exchange. Note that in this design, the master node becomes a single point of failure. So if the master node fails, then the whole system will be down. The master node typically does not constitute a bottleneck because the load on the master node is quite limited. So it's just taking the user connection requests and managing the compute nodes, but the real operation is going on in the compute nodes. Typically, the master node is not running the applications, so it doesn't have a high CPU utilization. Grid computing is somewhat different. Note that in the case of cluster computing, we would like to have the same operating system and also the same or near identical hardware over here so that we can manage these easily, and it wouldn't matter on which compute node a process is running. Whereas in the case of grid computing, the nodes are heterogeneous. Moreover, they don't even typically belong to the same organization. So it could be that, for example, a couple of computers from this university, a couple of computers from another university, maybe some computers from a research center or a research institution like the National Science Foundation or TÜBİTAK in Turkey. These could be collected together under a grid computing network. So actually, the individual devices are at different organizations. So they're dispersed across several organizations, but they work as a unified system. But since these belong to different institutions, they could be completely different hardware. Everything could be different. And we could be easily spanning a wide area network, whereas in the case of a cluster computing system, these are typically even in the same data center. Now, we have multiple organizations, and we're trying to pick a few servers from these different autonomous organizations to work together. So typically, we set up a virtual organization that spans these several organizations and includes only these nodes that are in the grid computer. So now we have some issues like identifying which computers are there, which users have access to which computers. But the basic idea is like, if we form such a federation, users in this university can benefit from all nodes in this grid computing network in all universities. So the idea is like, if we unify our sources, we will all benefit from this, because not all users will be using all resources all the time. So you can benefit from that statistical multiplexing factor there. To achieve grid computing, there are different approaches, but a significant proposal is about this layered approach. So there's the fabric layer, which actually interfaces the local resources. So this is typically also the hardware, but not only the hardware. So there are interfaces for all these resources. The resources could be the processors, the data storage, and others. It's typically used for querying the state of the resources and also their capabilities, because these are different resources at different institutions, remember. And while operating, you might, for example, at some point in time, you might need to lock one of the resources and then, of course, release the resource, whatever. The connectivity layer handles the communication protocols between these resources. And also, you need to do authentication both for the resources and the users. So it's also dealing with the authentication. The resource layer takes authentication service from the connection layer, but it handles individual resources. But the resource layer, each resource layer handles a single resource. That's the important thing. These resources could be, for example, creation of processes or reading, writing operations on the data, whatever. The collective layer now benefits from the authentication coming from connectivity layer and also the communication protocols coming from there, and also the resource management from the resource layer. But remember, we need multiple resources. So the resource layer was handling single resource for each resource, whereas the collective layer is a combination of them. So it handles multiple resources and also provides services like, you want to discover what resources are available and where. So discovery of them, scheduling of the resources to the processors, if necessary, the replication of the resources, blah, blah. And the applications are communicating only with the collective layer. So the application contains the real grid applications for a single organization. And the lower layers are providing service to the collective layer. Now, when we come to cloud computing, we can consider it at 4 different layers as a hardware, which is typically the memory, CPU, disk, and bandwidth provided by the network interface. The infrastructure, which is the computation infrastructure, so typically provided as virtual machines, and also virtual storage provided over over here. Note that the disks are here, but you provide, for example, volumes over one or spanning one or multiple disks. So you could have multiple logical volumes on a single disk, or you can have a logical volume spanning multiple disks. All these are handled by the infrastructure. So it's the data centers that provide the hardware, whereas services like Amazon S3 or Elastic Compute 2 of Amazon, these are examples of the infrastructure. On top of that, we have the platforms. So these provide, for example, the software platforms like Java, Python, or .NET, depending on what type of platform or what type of framework you want to use, and also the databases. So examples of this would be Microsoft's Azure or Google App Engine. And on top of that, you can have applications. These are web services, multimedia services, or business applications. Examples of these would be Google Docs, Gmail, YouTube, Flickr, whatever. So note that we can look at this from a different perspective. We talk about IaaS, which is the infrastructure as a service approach. So the data centers and Amazon together provide us infrastructure as a service. Then if you're using infrastructure as a service, they will provide you actually the virtual machines and the storage volumes. On top of that, you run your own platform. So it is up to you to set up and configure and manage your platform. And then on top of that, you run your own application. Or an alternative could be, you might say, I don't want to bother with managing my framework. So I don't want a simple virtual machine, but I want a running platform. So this is like, I want to write a Java application and be able to run my Java application, but I don't want to deal with maintaining Java. I just want to run my application. So it is up to the service provider to provide me the hardware, the virtual machines on it. All migration and other issues are provided by that. They will also provide you Java virtual machine. Everything will be provided. You just write your own software, your own application. Or you can also get software as a service. In this case, you even get the application. Example would be Gmail. When I say Gmail, for example, you can have your own institution running Gmail, of course, with your own domain name. So in domain name, it appears as mycompany.com, but actually it's running Gmail. And you don't need this time to care about the hardware, care about the virtual machines. For example, you might need, depending on how much email activity you have in your company, you might, for example, need multiple email servers. But Gmail will be taking care of that. You're not even aware of that. Okay? You're not installing any software. You just say, this is my domain name, these are my users. You just create their accounts, and that's it. Google takes care of all of it. Or, for example, you get the Google Suite. So it comes with Gmail and Calendar and also your Google Drive for the company. So all your users are using Google services over there. You don't maintain any application. You don't write one single line of code. All you do is you just specify your domain and open the accounts, and that's it. So that would be the case for software as a service. So if we discuss these layers in more detail, now here we have those layers once again, but in the reverse order. So the hardware was at the bottom, here we have it at the top. So the hardware is the processors, routers, power like UPS, cooling the AC system. All these are provided by the data center, and the customer never gets to see these. You don't touch the hardware, you just access it remotely. For the infrastructure, yeah, on top of the hardware, they also provide you a virtualization system. So you just have the virtual machines. Again, you access your virtual machines remotely. It evolves around allocating and managing these virtual machines and also virtual storage devices. Uh, when we talk about platforms, it provides you higher level of abstraction for storage and processing. So Amazon S3 storage system is an example of that. It just provides you an API. You just place your files in what they call buckets, and that's it. You don't care how it's managed, how it's backed up, what happens if a disk fails, whatever. All of these are managed by the platform. Or you might get the applications as we discussed. So they could be text processors like Google Docs and spreadsheet applications, presentation applications, email. All these services are there. Now, is cloud computing cost effective? Now, here we have an example approach for calculating whether it is effective or not. So we're going to discuss that. But before going into that calculation, let me just mention why cloud computing might be effective. And the reason is the following. Normally, if you try to do things in your own company, you buy your own hardware and you manage all of them. Now, the cost for you would be the following. Now, first of all, you have to purchase the hardware. Okay, you have to buy the server, you have to buy the storage system, you have to buy your routers and switches, all of these. The second, so this is your capex. The second cost is your OPEX. So CAPEX is capital expenditure. So the price you pay for these devices is your CAPEX, your capital expenditures. OPEX is the operational expenditures. So, for example, you need at least one network and system administrator. In a large company, these would be two different people. Network administrator and system administrator would be different. But if it's a small company, typically it's the same person doing both. But for example, if you need to provide service 24 hours a day, 7 hours a week, even during the holidays, in that case, for example, for each position, you typically need to employ 2 or 3 people. So that means you cannot survive with one system administrator. You will need multiple system administrators so that one's always available. If one is sick or on vacation or whatever, the others should take care of it. So you do have a lot of operational expenditures. And in the operational expenditures, it's not only the salaries, but for example, you have to, now in the CAPEX, I also mentioned UPS. If I forgot to mention it, I should. You also have the cost of, you should buy UPS, you should have the generators, you should have a good climatization for cooling the systems. And these also should be in replicas because one might fail, so the system should be still working. So all these increase your capex, but also they increase your opex because they cost you a lot of energy and this and that. Now, this way, your capex and opex will be very high if you try to provide a good service available all the time. However, you might not have so many customers, especially in the beginning. So there will be too much cost, but not much income. So that's one major problem. The other one is as the number of subscribers, your customers increases, okay, that's good, you're earning money now. But now the problem is, as the number of subscribers increase, the demand also increases, and you need even more hardware. And also, if your subscribers are distributed over the globe, now you have to replicate your data center in Istanbul, in London, in Amsterdam, in US, in China, whatever. And this duplicates your capex and opex. Okay, so this might become quite expensive. And unfortunately, you will realize that the utilization of your hardware is actually low. Because, for example, when people in China are using your services, actually your servers in US are sitting idle because those people are asleep. Or at some point, there might be too much load due to any reason in one geographical area, but not at the others. But still, you have to pay for the capex and opex in all of these data centers. Therefore, it is possible that, and not possible actually, the reality is that you have to make the expenses for the maximum load, but you observe that maximum load only once in a while. So suddenly the operation itself becomes extremely expensive. However, in the case of cloud computing, the cloud computing service provider has many customers like you, and your peak typically is not occurring at the same time with the other companies that are customers of this cloud computing service provider. So when you have high load, probably someone else will have low load, and vice versa. So the cloud computing service providers benefit from statistical multiplexing. That means benefit from the fact that not all customers are at their maximum loads at the same time, so that these service providers, the hardware and software they provide is actually not the sum of all of these subscribers. That would be sufficient. Anyways, let's come to the calculation over here. So let's consider some enterprise applications modeled with multiple components. So the application itself is composed of multiple parts. Each one will be a component, let's say CI, and each one requires NI servers. So now our application is actually a directed graph between these component CIs. So component CI needs to interact with component CJ to achieve the task ordered by the application. So we have arcs in between, so it's a directed graph. So if we consider two components, CI and CJ, we will call the number of transactions per time as Tij. So this is the number of transactions from CI to CJ, but it's just the number of transactions, pay attention. And the amount of data will be Si, Sj, just between these two nodes. And this is, now these are, remember, the slides of your book, so they are in PDF, I cannot edit them. But it says in total, but actually this is per transaction between Si and CI and CJ. So now we have the question in mind as, should we migrate some of our components to a cloud service? Now pay attention, we are not moving all of them. We are moving some of them. Now you might ask why we are not moving all of them. Now this is a more generic calculation. So if you wondered what will happen if you move all of them, you will make the number of components that are local as 0. Thus, all of them will have been moved. But here we're talking about a more generic case. So some of the components remain local. Local means in your company, and some of them are in a cloud service provider. So let's say out of these NI servers for component CI, we we get only lowercase ni at the cloud service. Therefore, uppercase ni minus lowercase ni will be the number of servers you still need to keep in your company. And by the way, as you have realized, we consider multiple servers for each component because of the load. We are trying to distribute the load. So what are the requirements in the migration plan? Of course, you should look at the policy constraints. For example, you might have things like, okay, you cannot move these because there's personal data in here. So due to GDPR, you cannot move it to the cloud. You might have such restrictions. And other restrictions also might apply. Note that when you move a service from local to cloud, then the delay typically will increase. And all transactions should continue to operate correctly. So requests or data should not be lost during a transaction. That's also a requirement because some of the servers are outside in the cloud service. Anyways, we will call be the benefit of migrating a component from local data center in my company to an external cloud service provider. So for compute intensive components, we'll call that BC, and for storage intensive components, we will call that BS. Similarly, the number of migrated components will be MC or MS. So obviously, the overall benefit is BC times MC plus BS times MS. So how about the traffic to or from the cloud? So from the cloud to the outside internet, our internet cost will be for all components, the traffic from the user to component I, so not the traffic, sorry, the number of transactions per times, sorry, the average amount of data that is to be transferred in such a transaction. Okay, so of course from transaction to transaction it could be different, so you should work with averages. So we will now define CI local as the number of servers for that specific component CI that are in our local data center, and CI cloud is the number of servers or the set of servers that are at the cloud for the same component CI. In other words, as we mentioned earlier, for the same component, some of the servers will be in our local data center, whereas the rest will be at the cloud. And we assume traffic distribution is the same for local and cloud, just for the sake of simplicity. So the number of servers in our local data center, remember earlier we called that NI, so CI cloud, the size of the CI cloud set is actually NI. And we will call the ratio of our servers at the cloud over of all of the servers for that specific CI as FI, so that's a ratio. So the overall traffic from I to J would be defined as in here. This is actually for two components, CI and CJ. If they're both in the cloud, that would be the now this is the all traffic, okay? So you should weigh it by the percentage of our servers for CI in the cloud times the number of servers, the ratio of servers in the cloud for CJ. Whereas at the other extreme end, both servers are in our local. So the ratio of our servers that are local would be 1 minus Fi for Ci, and for Cj it would be 1 minus Fj. And these constitute the weight of the traffic that is between two local servers in my own company. So this is the traffic between the servers for Ci and Cj in my company, and this is in the cloud, and these are in between. So let's call the cost of per unit of the cost of transmitting, say, 1 megabyte of information for the local and to the cloud. So the overall traffic would be a number of connections times the size of each connection. That means the amount of data that's being transferred. So the this is for the local to internet, and this is for cloud to internet. So your overall cost of moving some of your servers from local to the cloud would be this formula, whereas this part, actually the part in the parentheses over here, is actually the difference between TR local INET is the original when everything was in your company, and TR local INET star is after you have moved some of it to the cloud. So whatever is remaining, so that's a difference of what is being moved and what is remaining. So this will be our overall cost, and you should make your decision according to that. But note that this calculation is a very rough calculation, and there are also other factors like can you really handle so many servers? That actually becomes a more important cost than this over here. Now, so much with the high performance distributed computing. Now we switch to the second type of distributed systems, which is distributed information systems. So lately, network applications have emerged. So companies have to make use of multiple applications to achieve their tasks. So the applications are typically working in client server mode, but the important thing is now things have turned into application to application communications, which leads to what we call as EAI, Enterprise Application Integration. Let me give an example of this to make it clear. For example, let's say you want to start a company which sells goods over the internet. Now, you have one system, typically, for example, you purchase this. You have a system that is managing the purchase operations over the web. Okay, so people, your customers are connecting to your website, they're choosing the products and then purchasing them. So one application manages this. But these goods are in your storage, so you have to manage your inventory. When you sell a product, it's no more available. Okay, even if it is still not distributed to the customer, it is sold now, so it should, you should decrease it from your inventory. So there is an inventory management system. And also, you're going to send these goods to your customers over some carriage service like FedEx or in Turkey, Yurtdışı Kargo or whatever. These are the carriage services. Now, first of all, the carriage server, FedEx or Yurtdışı Kargo, has its own system. It's not a code you have access to actually. You just have the interface to that. The other one, for example, let's say you bought some code from SAP, as you just purchased an ERP system from SAP. For the other part, you purchase some software, say from Salesforce. So you have to integrate Salesforce application, SAP's ERP application, and over here, some maybe carrier service application. So now we have the integration of the applications at the enterprise level. So to do this, you will need some transaction protocol. So very simple primitives like starting a transaction, ending it, aborting it without completing regularly with end transaction, just cancel it, reading data and writing data, such things. Now, but what we realize from the EAI description we just had is actually when you're trying to do something, actually it's composed of, your transaction is composed of sub-transactions. So here we have another example. You try to book the plane and the hotel as a single package from your travel agency. So you connect to the travel agency's website and you pick the airline and the hotel together. But these are actually two different companies. One is the airline company. Your travel agency is not the airline company. They're just selling the tickets. The airline operator is some other company. And they're also working with other travel agencies, not only your agency. Similarly, the hotel is a completely different institution, a different company. So these are separate sub-transactions performed over different systems. But altogether, from the user's point of view and also from your company's point of view, it's a single transaction. It's all or none. So such operations should be atomic. So you either book both the plane and the hotel, or you don't book any. So it should be atomic. It should be consistent. So the system invariance should not be violated. That means when you start the transaction, the system should be in a stable state. When you end it, either by regular end or by abort, everything should be stable. Either the services are sold or and it should decrease from the inventory, or nothing is sold. They should be isolated. They should not be interfering with each other, especially different customers should not be interfering with each other. And it should be durable. That means when you do a commit, it is it. It should be permanent. You shouldn't be losing any data. So to achieve such operations, especially when you have multiple servers behind, typically in front of these servers, and these servers could be your own servers or they could be servers from other companies, as in the case of airlines and hotels. In front, you will have a transaction processing monitor. Okay, so the client connects to the transaction processing monitor. It will interact with the correct servers, send the requests, get the replies, maybe also before giving a reply to the client, also connect to this server, also get a response. When you get both of them, then you reply to the client. So it's the transaction processing monitor that's taking care of it. Another approach could be having a communication middleware. So the client applications connect to the middleware, and the server side application is over here. So the clients do not directly connect to the server side applications. They even don't know how many server side applications there are, where they are located, whatever. So to achieve this, for example, you might make use of remote procedure calls, as you might have discussed in CMPE475. So it's like a procedure call, a function call, but the function is not running on your own computer. The function, what I mean is the following. The client application is a program running here. So it makes many function calls, but some of those functions are not running on this computer. They're running on the server, actually any one of these servers. Okay, so the client acts as if it's making a local function call, but the function call goes over RPC. It finds the correct server over here. Let's say this one. It will connect to this one and pass the parameters for the function call. And the RPC stub will call the correct function here. The function will be executed. The function will return the return value of the function to the RPC stub here, which will pass it to the RPC client here, which will pass it to the client application here. So from the point of view of the client application, it appears like it's making a local function call, a function call of the RPC client over here. But actually it's getting executed on a remote machine. That's why it's called the remote procedure call. But we are hiding all these details from the application. Of course, it is far slower compared to a local function call, but still you're able to execute functions on a remote machine. There are also other, there's the concept of RPI, which is actually RPC for object-oriented, but it's almost the same thing. Or you can have MOMS, message-oriented middleware. So you send the messages over the middleware. The message arrives at the destination. The destination retrieves the message from the middleware and works this way between published message boxes and subscribed applications. How do we integrate the applications? One way is through file transfer. It's simple, but it's not very flexible. Now, first of all, the file formats and the layouts should be the same for different applications. The file management should be, again, compatible. And you should be updating the propagation and notifications to both parties. So you need extra work to do here. And as we said, it's not flexible. Another approach is sharing databases. Database management systems will handle most of the work here. It's much more flexible because the EBMS system is handling the details, but still requires common data machine for both applications. And that might become a bottleneck. The other alternative is remote procedure call, RPC, as we have discussed. It's effective when you're executing actions, especially in a series. One action, then this one, then this one. So it's just like running a program. And messaging. The problem with RPC is that to make an RPC call, both the client here and the server should be up and running at the same time. When the client connects, the server should be up and running so that it can respond. And when the server function completes and returns the return value, the client application again should be up and running. Whereas in the case of messaging, it could be that you just send your message to a message box. When the server becomes available, it will access the message box and pull the request. So they don't have to be available at the same time. But of course, this brings decoupling in time and space, but also adds delay in the process. So that was with the distribution of information systems. Finally, we come to the pervasive systems. So pervasive systems are typically meant for either mobile systems, as we're going to discuss, or for IoT systems, Internet of Things systems. So the idea here is actually the system is always and everywhere. That's what pervasive means. Pervasive means actually everywhere. So this time, the system blends directly with the user's environment. We're talking about, for example, sensors in the environment. Okay, so it's a cyber physical environment. It's cyber, but also physical, in your real living environment. So we talk about ubiquitous computing systems. They're, as we said, pervasive and always present. So there is continuous interaction between the system and the user. The other one is mobile computing. Well, that's also pervasive. But this time what's different is in ubiquitous computing, we don't necessarily have the movement of the user and the device. Whereas in the case of mobile computing systems, as the name implies, they're mobile. It's inherently mobile. So the user changes location, so you also have to keep track of the location of the user. And finally, in the sensor and actuator networks, they are again pervasive, but we do have sensors all around in the environment. So you're continuously collecting data. That means you're doing sensing. And depending on whether it's just a sensor network or if it's a sensor and actuator network, in that case, you might have an actuation to the environment. By actuation, we mean, now in the case of sensing, you just collect the data. In the case of actuation, you also modify the data. For example, in sensing, let's say you're sensing the temperature, and if some building in the campus is too cold, then, for example, you turn on the heating there, and that's actuation. Because this time when you turn on the heating, you're changing the environment because the temperature in the system now changes because of your action. That's why it's called an actuation system. The core elements here are one, distribution. So the devices are networked and they're fully distributed all over the space, all over the environment. Interaction. So there should be continuous interaction between the users and the devices, and that should be invisible. The details should be invisible. The system should be aware of the user's context and optimize the interaction. For example, especially in if there is, for example, mobility, you should be aware of where the user is. And then, for example, provide necessary services to the user in that specific area. Autonomy. So devices are actually autonomous from the user, from the human intervention. Therefore, they should be self-managed, self-configured, managing all of its operations. And the system typically should have some intelligence so that it can handle a wide range of dynamic actions and interactions, as we've discussed. In the case of mobile computing, well, it is ubiquitous computing actually, but the difference is now we have mobile devices like the smartphones, tablets, GPS devices, remote controls, or active badges, like you can have name tags, and the system might be following where you are. And depending on your location, for example, if you're in a factory and if you're very close to a machine that might harm you, in that case, for example, the system should turn off that machine so that it doesn't harm the employee. And one other thing is we have a very large set of devices. So the number of devices suddenly explodes. It's not like the number of desktop computers we have. The mobile also mobility implies a change in location. So we should have a discovery mechanism to find the local services and reachability. For example, wherever you are, when you say print, it will be a printer nearby. And the communication may be difficult or at times, so you may not have stable routes because you're moving, so the route is continuously changing. So therefore, the quality of service is also changing. You may even have times when you're not connected at all. So we should have some disruption tolerant networking. So one important thing is we should be tracking user mobility patterns. That means how do the users move? Well, luckily, the users tend to repeat their actions. Every day leave home and come to office. On some days it could be different. Some days you might be coming late or leaving late, or you could have a vacation, so your regular behavior changes when you go to a vacation. But in general, we're repeating this. Now, especially when the networks are not always accessible, in other words, like if you don't have, for example, a cellular network that provides ubiquitous communications, in that case, you might make use of some other ideas. One is the packet switch network. Now, there's no typo. It's not packet switch. This is packet switch. The idea is actually what we call disease spreading algorithms. This time it's not disease, but it's data. So, for example, Alice wants to send a message to Bob, but Bob is not in the direct communication range of Alice, and also we don't have, as I said, a network like a mobile network over which you go to the base station, and Bob also goes to his base station, and the base stations are connected to each other. There's nothing like this. Okay, in such a scenario, for example, one solution. So in other words, there's not an underlying network. One solution is Alice gives her message to her friends or maybe some strangers, and as they move around, if they see Bob, they give the message to Bob. This is called packet switch networks. So this is like you put the data into your pocket and you move around, and when you see Bob, you take it out of your pocket. This is also called disease spreading, and there are variations of this. Like in some of them, only the friends carry the message, whereas in others, anyone can carry the message. But you should be careful with these disease-based approaches. The number of messages in the network, they get replicated, and at some point it might explode. So you should also have mechanisms for taking care of this. The observation is that such approaches work when you have a community of friends. So what is a community? A proposed approach here is you have a community, related people, but you also have a familiar set, which is a small, a separate set, but not completely disjoint. So these are the people you're familiar with. Okay, so you know at least that person, at least by the face. Whereas the community set is, people like in your, let's say, project group. Okay, so these are your friends in the classroom, but these are specifically your project teammates. Okay, so what happens is when node I meets node J, it will decide to add node J into the its community set, its close friendship set. If the familiar set of J intersection community set of I divided by the familiar set of J, you look at this ratio. If that's beyond some threshold, lambda, then you decide to add J into community of I. This actually means the people J is familiar with, if that intersects with my community set above some threshold, so like the people J is familiar with, if many of them are in my community set, then J deserves being in my community. So this way you actually increase your community set. And when two community sets intersection is very high, with the gamma multiplied the union of these two community sets, then you also merge those two communities into a single community. And according to the experiments, 60% is the threshold there. Okay, we mentioned the mobile patterns. How mobile are people, by the way? Especially when we talk about these disease spreading algorithms. Because if no one's moving around, for example, disease spreading algorithms will not work because you don't go anywhere. So how mobile are people? Experiments and collection of data shows that it's decreasing like this. So people moving at lower speeds or lower distances are more. People do not move too much. Okay, people tend to return to their same place in 24 hours or 48 hours or 72 hours in 1, 2, or 3 days. That means actually you return back home. Well, you go to your parents' home every few days or to your friend's home. You visit, you happen to be moving around some limited number of places most of the time. You rarely go far away. Now, for the case of sensor networks have been studied a lot in late 2000s, around 2010. It was a very popular field, but not anymore actually. But still with IoT, we have similar approaches. So there is some overlap between IoT and sensor networks. So we are talking about tens or thousands of sensors, sensor nodes in the field. These are very simple devices. They have very limited computing and storage capacity, and also communication capacity, very short-range communications, and also battery capacity. So these are very limited devices. These are just sensors you deploy, for example, in the forest or in open field or inside the buildings also. So you have a huge number of sensors in your sensor network, and we have some what we call sync nodes, one or more sync nodes that are at operator's side or close to the sensor network. Sometimes we put these sync nodes in the middle of the sensor network, but a small number of sync nodes which collect the data. So the data flows to the sync. That's why it's called a sync node. One approach is every node sends the information to the sync. Sync collects all the data and then processes the data. Or another approach is the sensors are capable of doing some processing, and from the operator, a query is sent to the sensors. So rather than the sensors periodically reporting to the sync, this time the operator sends a query saying, for example, what is the temperature? Or have you seen any large animals in the forest? This kind of query is sent, and the sensors, at least those that have seen such an animal, for example, or at least the sensors where the temperature is above some limit, which might show a fire in the forest, they will be responding, okay? And for example, when you're taking, say, the temperature, you would like to see actually the average. So one sensor might be making a mistake, so you get the information from multiple sensors in this area, and you take the average. That is called in-network processing. So you send your temperature here, this one also sends it here, and this one takes the average of its measurement and the measurements of these two, and then sends it to this one. So it works that way. The sensors, or in the case of IoT systems, the IoT nodes, cannot stay up and running all the time because they have limited energy. So they have a duty cycle that is actually the percentage of time they're up and running. Note that, okay, you can guess that data transmission takes consumes energy, but interestingly, receiving or at least listening to whether there's transmission or not, it consumes almost the same amount of energy. So there's not much difference between transmission and reception. So we have to preserve our energy because otherwise soon all devices will run out of power, and you just have to deploy a new network, which is not manageable. So our nodes are active for T active duration, and then they're suspended. That means they're sleeping during the T suspended duration. So T active plus T suspended is the old time, and T active is the time you're active. So this ratio is your D2 cycle tau. And the typical D2 cycle is 10 to 30%. Typically, in, for example, IoT systems, it is as low as 1%. When nodes are not always active, then let me go back to this network. It's easier to explain over here. Now, you want to communicate between these nodes. Say this one's active. Consider a time duration of 10 units. Okay, so from in the first time unit, this is active. The second time unit, this is active. This is the third, this is the fourth, fifth, sixth, seventh, whatever. At different time units, these are active. Other time units, they're just sleeping. So when this one wants to send something, everyone around is sleeping. So nobody receives its transmission. Okay, so we have such problems with the sensor networks. We cannot stay alive all the time, but if we sleep and wake up periodically, the time you wake up, there could be no one around. Or at least you can talk to the people only that are awake. So, especially when these things are periodic, it could be like some nodes never connect to other nodes. So, and also one node is not capable of doing much stuff because we said these are incapable devices. So we want clusters of these devices to do useful work, but constructing the clusters will be difficult because these are sleeping at different times. So there are mechanisms, there are millions of papers written on sensor networks, but there are many proposed different approaches for forming clusters. But most of them are troubled with this approach, as I mentioned. So that will be the end of this chapter.